I want to talk about a bit how do we test the concurrent and parallel code, how to make sure that the tests do what they do and do what we want them to do. And then I want to talk briefly, or not briefly, a bit more about property-based testing. This is something relatively less common in Go, but I find it very useful and very interesting. So, does it work? Doesn't seem so. No? Yeah. All right. So why do we even test in Go? So basically what you can say is we test to see the difference between a 0 and a nil. It often happens that some small bugs show up in our code that we don't know about, that can be shown by proper testing, thorough testing. We had a situation where if we had a good thorough testing of our code base, we would have caught the difference between 0 and a nil. That difference means removing or not removing the information from the database. If you have a model or a model that should be a pointer, but it isn't, and it's a timestamp, it's going to put a 0 timestamp, which is far back in the 70s, right? And then when you clean up all stuff, you're going to remove everything that you shouldn't. And if we had proper testing, we would have got it, right? So I want to go through some examples, show you the code that is there and how you can test this code more effectively. So let's go then. Let's see. Again, wrong button. All right, so Go is a bit different when it comes to testing, or rather how you structure tests. In most languages, you usually have it like separated into, let's say, classes or separate functions, separate test functions that run this one by one. But in Go, the usual paradigm is to create a single test or single functionality, and cases are put into a structure. It's usually a slice of structures where each element of a slice is a test case, right? But why do we do this? So usually Go isn't that nice when you look at it holistically and you see just a function that is that long and has everything jumbled up, right? So this structuring allows us to separate the cases to be more easily readable. Right? Then if you want to add or remove or modify something, it's easy. You don't need to check the entire test. You just check the test case itself. And this also allows the better organization of those tests. And of course, having this means that we have just one piece of code for the test itself that can be reused later on. Right? So if we don't need to write the same code for each test case. We have just one code and everything there. This is not specifically used by structured testing, but it's easier to understand how it works with the parallelism of testing itself. I'll talk briefly about this a bit later on. All right, so maybe first example, how this looks like in practice. So like I mentioned, this is an anonymous structure, a slice of anonymous structures where you just name it, and then you have some parameters for those cases. Right? So this is a simple example of something that can be tested. Let's say we have this function, can be executed in parallel, so we can encapsulate this in some execution that can or cannot be parallelized. I'm pretty sure that this is not needed anymore since 1.22, but it's here because I'm used to it. But this fragment tells Go that this specific test case can be run in parallel. What's going to happen when you run it? There's a comparison of those tests, one run without parallelism and one with. As you can see, the difference in time execution is somewhat visible. As you can remember here, I can't see it here, but the function itself, it's just a simple function that just sleeps for a second for the sake of example. So you can see that in first test, it runs first case, second case, and so on and so forth. In case of parallelism, it checks what can be run in parallel, pauses this, saves it for later, runs the rest of the test, and at the end, runs everything at once. Thanks to which it's faster. All right, but there's one thing that you need to deal with in Go that is not present, let's say, in Python. In Python, you have functionalities like setup and teardown that can be globalized for a class, for a single test, for entire modules. In Go, we don't have this, so there's different ways we can achieve this. From the most simple ways, like a normal simple custom function that sets everything up and then tears down, but doesn't give you a lot of flexibility. There is something interesting like T cleanup in the system library that allows you to just clean up after every single test that is run in the suite. This is great if you don't care about setting anything up, but you have to remove some data from the database or something like that. And my personal favorite is the setup and tear down per test case. So I usually drop a setup and a tear down function or definition of a function in the structure itself, and then you can juggle it per test case. This allows you to have different expectors in each test or in each case, and it gives you the most flexibility. There's also way more different ways you can do it. Okay, you can put the setup and tear down in context, or you can control it by environment, all different kinds of stuff. So let's talk briefly maybe about the best practices, right? These are the, let's call it canonical rules, what is good to follow to have well-defined and well-functioning tests. I will not be going over all of them. I just put it there. You will have access to them later on. It's not like a law that you have to follow, but at least having this in the back of your head when you're writing tests will help you tremendously in the end. Okay, so this was like, let's call it an entry to this. Let's talk about testing parallel code. So there's certain problems that don't show up when you test normal linear functions, right? They show up when you run multiple copies of the same function at the same time, right? Sometimes you can run a test and today it's going to pass, but tomorrow it's going to fail. We don't want that. We always want to have the test that will be deterministic, that you will always have the expected result. We want to be able to, in those tests, also detect any form of potential deadlocks and potential race conditions. Because what's better than the test to actually detect this, right? And tests ideally should also check whether or not different parts of your code mingle between each other and change its behavior based on the order of execution or how long they're running and all this stuff. Finally, especially when running multiple workers or multiple Go routines, you have to make sure that everything is properly cleaned up after that. Okay, so let's talk maybe about the timing first. So here's an example of a structure. The point of this structure is to gather results of different Go routines. So it responds to a Go routine, and as it finishes, it loads its result to this aggregator. Here we have an example function that adds this result with appropriate sig primitive, right? And we have also a function that basically displays all the, or lists all the results that have failed, right? So you can have a look into them. So we could write a test that effectively just does this. It creates some aggregator, we spawn multiple Go routines. Here we simulate work, but let's say that something happens in that time. And once this work is done, we add this to the result, right? And then at the end of the test, we want to see that we got no errors. There's a problem here because this test will always pass, right? Because we have not waited for the Go routines to actually finish. right? So it's very important that if you have parallel code, that you should always wait for all the routines that you have to finish, or that you are interested in, let's say, to finish. And of course, there's multiple ways to do this. You can do it with channels, you can do it with weight groups, choose your poison. Okay, so it's a bit more problematic with deadlocks, because if you have multiple parts of the code and they interact with each other, detecting where they are can be a bit more complex, right? What you will see eventually is that the test runs infinitely and never ends. So we have another example here. We have some bank account. We want to transfer from money from one bank account to another, right? I've added here a millisecond to allow for context switch so that routines can go between each other. And if we just run it like this, we of course added some primitives to wait for the routines to finish, but they never will, because they're going to deadlock on the mutexes, right? So what we can do about this? We can try, manually debugging and trying to find this. In this example, it's simple, but if you have a nested structures of different packages interfering with each other, it might not be as simple, right? So there is a package called Go Deadlocks that is a drop-in replacement for the normal mutexes. And what it does, it detects the order of the initialized mutexes. So when you actually run the test, it allows you, it shows you that there is a potential deadlock that can happen. So it's worth using if you have a lot of code that interacts with itself. Okay, so race conditions, thankfully, are now, or detecting race conditions, thankfully now is supported by the standard library. So let's say we have this a simple piece of code, right? So we're running some loop and we are incrementing the counter, right? And we can probably see where it's going to go, because we don't really wait for multiple threads, or sorry, we don't lock the variable, the counter variable, before we increment it, right? So if multiple threads try to write to it, it will happen at the same time. Nothing is going to wait, and you're going to have bad results. So let's have a look at the results. At the bottom, we see that we expected to see 10,000 is the sum of everything, right? It should be 10,000, but it isn't. It's because both threads at the same time read the variable, both of them incremented at the same time, and one of them stored just before the other, and you have just lost a value, right? So I strongly suggest to use minus race in your test suits when you run the test, I don't know, in your CDCI or something like this, because this will show you that there is a data race, right? Even if you don't specifically test for this, but your program uses some form of parallelism, it's worth enabling, because it can find this in most unexpected places. All right, and the most interesting of this, in my opinion, is the property-based testing. So this is a fairly new concept in Go, and it revolves around defining properties of the function or method that you want to test. The methods have specific behavior that you expect of that function to have. So an example, when you have a class of a rectangle, you expect that this rectangle will behave like a normal rectangle. It's going to have positive width and height, and the area is going to be always positive, this kind of stuff. This is like a descriptive way of your class, what it should do. And property-based testing is kind of like fuzzy testing, in a sense that it takes multiple inputs, generated inputs, feeds into your function, and check whether those properties hold. Right? So let's say, we'll see in a second in an example how this looks in practice. Right? So generators are, I mentioned here generators, but probably I'll skip it now and show you later on how this looks like. The downside of property-based testing is obviously the test will run longer, right? They have to execute the same function over and over again for different inputs. So they will take longer. And especially if the function itself takes a long time, it's going to be linearly takes longer. Okay, so let's have a look. I mentioned rectangle because there's an example. And I've taken three example methods here. One that returns the area that we want to see, so there's no parameters to the function. One that scales the rectangle by some factor, so there's one standard parameter, and one function that adds additional rectangle to this one. So this is a parameter that's more complex. This is a structure as a parameter. So how can we define this? How does this look like? So there are basically two options. Maybe there's more, but I haven't seen it. There is in standard library, there is a package called testing quick, which has like a very basic implementation of property-based testing. So what you do is you define this property, right? So area should always be non-negative, right? So this is what you want. And you define a function which is basically a predicate, takes some parameters and returns a Boolean value. And inside, you say whether or not for this input, that property holds, right? And for example, here we have for different types for the rectangle, right? So it's very similar. You want to tell the property what actually happens, what you expect to happen, right? And checking this is very straightforward. Since you already had this, you can check each of the properties that you defined and see whether they hold. For this, you can define different inputs, different lengths of inputs, how many iterations you want to do, and so on and so forth. An example here, you can see that it failed on some inputs. So now you see that for this, your function was not working as you expected it to be. So this gives you a hint that, there's something wrong with the implementation that I didn't expect. So this is the quick version. There is an external library that does this as well. It's called Piotr. It's great. It's fantastic. The idea is the same. You also define some property that should hold always true or not true, depends how you want to look at it. And it is slightly more unwieldy in using than quick, but it's because it provides you far more capabilities. Quick is, very short. You want to put it quickly, off you go, right? If you don't care about the details, or you have something quite fairly simple, you can use it. But if you have something complex that needs to be more thoroughly tested, and it's not easily, maybe not reproducible, but generated, the values are not easily generated, you probably want to use this. So the way it works is you define, similarly as before, a predicate that takes some parameters, as we can see here, and then you define the generators, right? So one that generates width and one that generates height in this example. So it's going to give you, it's going to run this predicate for all those generators. But this seems basically like one-to-one with the quick. But there are more ways that you can generate more complex structures. So for example, here, if we want to generate a rectangle, we can define a map that will be generated. It can you can put also the generators there as you wish, right? It can be custom, maybe a static or already predefined generators, but you can also create your own generators. So this creates you a generator from other generators. And this is what you can do with this. You can nest and compose different generators into one, so that you can have one generator for, let's say, nested structures, like deeply nested structures, right? And the testing is basically the same, right? Okay. Now this is something more complex. I think I forgot to include the code that it represents too, but I'll describe what it's for. So imagine that you have a function that takes two parameters, start and end, and what it does, it spits out to you a slice of values from to 2. So you're gonna, let's say if you have 50, if you put as a start, let's say 0 and the end 10, it's gonna give you a single slice with numbers from 0 to 9. And when you're testing and you want to verify different versions, you don't want to just define start and end. You want to test different combinations. So this is what the map and flat map will help you with. So map is a function that takes a generator. It can be any generator. This is here. Takes a generator and then as an input takes a transformer. It's a function that will take the singular values, transform them in a certain way, and spit out a value. Not a generator, but a value. So if you put this and you want to construct something more complex, the map will help you with this, right? So if you have, like in this example, it will just return you some range from start to finish, right? Now, what is flat map then? It's very similar in concept, but while map takes the range and takes the range and a transformer and returns you a value, flat map takes range, transformer, and spit up generator. So the difference is slight, but effectively with this, what you can achieve is you can combine different things or different types of parameters to have a long or large sample of different parameters. So it's a bit more complex example. And in this case, we didn't really, this is a bit counterintuitive because in this example here, the range is the function that we actually test, right? So this is what we're testing. And in the test itself, when you take the predicate and want to test it, you feed the generator that you created, but you just make sure that the rest fits, right? That you got to the slice that you expected. All right. And that's pretty much it, what I had prepared for you. So maybe I'll mention that all the code examples and the tests and all of that is on GitHub. So you can download it from there. There's some interesting articles that you can read about this if you're interested. And yeah, that's it. Do you have any questions?
I read a question from the application. Can we run fuzzy test in Go?
Yeah. So we can.
Yeah.
Yeah. So the Go natively supports fuzzing. It works slightly differently because normal tests, they just run and check the test cases one by one, while fuzzy tests, usually you run the code and it runs until it fails, right? So that it doesn't end when a certain number of cases are finished. But yeah, you can do it. You can run it. There's a good articles on GoDev where you can check it out how it's done. But it can.
Any other questions?
Good question. For the deadlock detection, you have to replace the type of the mutex, right?
Mm-hmm.
And
Yeah.
so, the question is, how do you deal with that in a large code base where, assuming that for production you would like to have the normal mutex and for testing you would like to have the deadlock capable detecting mutex?
Interesting question. So I would probably create a factory of this, so that when you have a testing environment, the factory is going to return you this mutex, and then when you have it in production, it's going to be the same mutex. That's what probably I'd do, but it's it's still a lot of changes, I suppose, right? Because if you have large code base, you would have to still find all those references to the original one and replace it. But yeah. Otherwise, you can just look at the test and try to figure out where it hangs. But yeah. Any other question? Yeah.
These generators, in the previous example, you had two generators from 1 to 1,000. So how many iterations it runs? Like 1 million or?
You can define the range. You can define each generator can have how many of those you want to generate, right? So the generator itself will be generating numbers, or numbers or properties or whatever have you. Right? But you can tell when you're running tests, you can tell with the configuration, it's not visible here, but one of the parameters for the testing property is additional configuration, which you can add, and you can define all different things. You can say that it has to run at least, 1,000 iterations, right? So it is possible to define how long you want to run it, or how many iterations you want to run.